Hi, this talk is about parts, a fairness correcting pre-processing method. What makes parts unique are these three characteristics. First of all, it is agnostic to both group fairness definitions as well as to different classification algorithms. Secondly, parts is parameterized, meaning that you can control the amount of fairness you introduce into a classifier. And finally, parts may be used with both single binary protected attributes as well as with many multi-class protected attributes as well. Parts operates on different group fairness definitions, and here I'll mention the three we used in our paper, but it may be adjusted to use other group fairness definitions as well. The first definition we used, known as demographic parity or equality of outcome, states that a classifier satisfies demographic parity when the probability for the classifier to predict a positive outcome for the unfavored group is the same as the probability of the classifier to predict a positive outcome for the favored group into the protected attribute. The second definition, equality of opportunity, is similar to demographic parity with the difference that we will only be looking at probabilities over true positives, not over the whole protected attribute subgroup. And finally, proxy fairness has to do with intervening the test set. We will basically do two different interventions, one in which every instance will have the protected attribute assigned to U, and another intervention in which every instance of the test set will have its protected attribute assigned to F. And then we will compare the probability for the classifier to produce a positive outcome for these two interventions, and they should be the same if we want it to satisfy proxy fairness. The problem with having different fairness definitions is that they are usually incompatible with each other. That means that if, for example, we want to achieve demographic parity, that means that we will probably not be able to achieve equality of opportunity or proxy fairness. That is the reason why we made our method parts behave in an agnostic manner, meaning that the user gets to decide which of these fairness definitions is the one he wants to enforce, and then he can optimize for it. The way in which our method works is through data resampling, specifically training set resampling. Looking at a very simple example here, we will have two possible outcomes, positive and negative, and we will have two possible protected attribute subgroups, which are favored and unfavored. In a typical setting, we will have a lot of favored positive instances, not so many favored negative instances, a lot of unfavored negative instances, and not so many unfavored positive instances. The way in which we can balance this is by either undersampling F plus and U minus, as seen here, or by oversampling U plus and F minus, as seen here, or by doing both of these things at once, as seen in this last figure. So we control how much we want to either over or undersample or do both of these things through a correction parameter D taking values from 1 to -1, where 1 means not touching the training set at all, -1 meaning reversing the positive ratios for the favored and the unfavored groups, and D equals 0, meaning that the positive ratios for both the favored and the unfavored groups become the same. This in turn will have an effect over the predictions over the test set, as may be seen here. And in turn, this change in predictions will have an effect over the different fairness definitions. In the particular case of demographic parity, we are looking for this point here, that is the point at which the green line crosses over the y value 1, or equivalently, the point at which the blue line and the red line intersect with each other. In order to find this optimal point, one way to do so is through Bayesian optimization, which is the method we have tried, specifically using the gPyOpt package. So this package will try out different possible optimal values, and based on the previous attempts, it will gradually improve its potential optimal value. Similar to all the other fairness correcting techniques, there will always be a fairness accuracy trade-off with our method. So what this means is that in order to achieve optimal fairness, the accuracy performance of a classifier will necessarily drop. The thing is, we want to make this drop to be as small as possible. As may be seen on the first two of these plots, actually there is not that much difference regarding demographic parity and equality of opportunity when choosing the sampling strategy we will be using, right? So it doesn't matter whether we use undersampling, oversampling, smooth, or preferential sampling. However, for proxy fairness, there is a slight difference. When using preferential sampling and smooth, the things are a little bit better. Comparing our method against the existing fairness correcting solutions, we can see that in an apples-to-apples comparison, that is comparing methods which use the same classifier, our method outperforms them in both fairness, which are the first two columns, as well as in accuracy. Actually, that is a second big advantage of our method, the fact that you can choose which classifier you want to use, and as we can see here, regardless of which classifier you choose to use, you will still obtain very good fairness and accuracy trade-offs. There is a little catch to our method though, and that catch is that our method's effectiveness is not that great when you have perfectly separable or close to perfectly separable data. However, when you're in that particular scenario, one thing that can be done in order to make the method effective again is to introduce some random label noise into the training set. Finally, I will quickly tell you about how to use our method with multiple protected attributes. So the main idea is if you have more than one protected attribute, you will combine them all into a single combined PA new attribute. In order to do so, what you do is you take every subgroup's positive ratio. For example, here we have the age group 20 to 30. We see that the positive ratio for that particular group in the training set is 20%. And then we compare that against the overall data set's positive ratio, which is 30%. So in this particular case, we see that this subgroup actually has minus 10% under the overall positive ratio. If we do likewise for every column, we sometimes will have negative values and we sometimes will have positive values. And when we add them all up, we will end up with a number, and whether that number is negative or positive will determine if the combined PA is unfavored or favored. In this particular case, since it's negative, this will become unfavored. And in a second example here, even though this instance belongs to the female group, which is an unfavored subgroup regarding this column, overall this instance may be considered as favored because on the age group and the country group and on the race group, it is considered to be favored. So the overall sum is plus, and hence this becomes favored. And as you can see here, this correction actually is quite effective. Over the adult income data set, we can see that if we correct for gender only, as on the left side, as we introduce more and more correction, there will be an increase in the gender's positive ratio, in the females' positive ratio. But on the other hand, all of these other unfavored groups will have either no effect or even a diminishing effect as correction increases. However, when you combine them all into a single protected attribute and then apply correction over the combined protected attribute, they will all show a benefit after correcting for fairness. So in conclusion, we have presented PARTS, a fairness correcting pre-processing algorithm. PARTS is parameterized, it is fairness, definition, and classifier agnostic. It is extensible to several multi-class protected attributes, and it's way competitive against existing fairness correcting solutions. Thank you very much for watching.